with the width. Yes. Yes, starter. Will I start? Huh?
Can you please add me on the Teams? Thank you.
Where to add? It's a tone. Did you got it? Is it okay now?
Yeah, it's okay.
Okay.
I will join Team as well. Yeah, it's downloading.
Okay. Oh, sorry. Yeah, maybe you have downloaded the software, so I'll show you EEG analysis. EEG analysis can be done in many different ways. There are so many software, open software in the uh, website, and the very popular website is EEG Lab, which is mainly used for the pre-processing and ERP-related analysis, and Field Trip, which is broadly used for the connectivity analysis and source reconstruction, and the what is brainstorm, which is basically used for the source analysis. But here I'll show you which our collaborators Sebastian developed software MOHAWK. It's based on we have a MOHAWK kind of connectivity, that's it. But it's a combination of three software. One is EEG Lab, which do all the pre-processing. So you'll be able to see in the background the EEG Lab structure, and then for the connectivity, it uses Field Trip, and for the network analysis, it uses as the BCT, Brain Connectivity Toolbox. And all the three toolbox are MATLAB-based toolbox. I don't know if it is now people have developed for Python or not. I think EEG Lab is not, both EEG Lab and Field Trip is only for MATLAB, not for Python. But when BCT, Brain Connectivity Toolbox, this is also there for the Python. So you can use also, and last time when I presented, I only presented the MOHAWK, but this time I'll try to present some function. So you could use those functions for your study independently outside to the MOHAWK pipeline. And last 15 minutes, we have already 10 minutes. Last 15 minutes, I'll try to show you the ERP analysis using what is Field Trip. Again, it's that we developed in our lab, so it's a little bit inorganized form, but it's do the job. It gives the ERP component and power spectral analysis and representation, and it's a semi-automated mode. So let's start for the MOHAWK is do only for the resting state. It doesn't do the task-based analysis. So we have many of paper using MOHAWK here, some couple of papers, and this pipeline is semi-automated. So semi-automated means we need to do manual ICA selections, sorry, noise component selection and ICA selection, and in the automated way it do the what are essential and standard. So the essential and standard is what is the pre-processing step, which is importing the data, and event the channel location downsampling, filtering, high pass and low pass filter, and it also automatically detect which are the channel or epochs are bad, and it also do the post processing automatically, that consist power spectral density, power spectral calculation, connectivity calculation, and graph theory, and it also provide visualization. But again, you could do all what is independently. So I'll show you when I'm presenting, that time I'll show you directly. So yeah, I think all people have downloaded the MATLAB, sorry, the MOHAWK now. So you could go to the app, and in the app you click the MOHAWK. Sorry, just one minute. So you can click what is MOHAWK. So it will show you which file you want to use. Currently, we can import the EGI at the raw file .raw format, or we can also import the MFF folder, or the blend product BHDR files. Those three we can import. So if you seen that this is the raw file, which is without means ECG and all these things, and this is look like what is a folder, MFF folder, which content, sorry, like event, and this is all other sensor and signal, this binary, which is EEG signal and other signals. And the brain product have a three file, unlike the EGI. So the .eeg is the raw signal, and the bhdr and bmrk is the header file, which contain the information of this. Sometimes what we do after we record the EEG signal, we change the name. So when we change the name of brain product, it doesn't detect in most of the software, including EEG Lab and the field trip. So we must not change the name. In case someone changed, so we'll get the error saying when we import. So for example, you import the BRH to BRH, and some the original name was BRH. So it will show BRH S2 BRH does not detect. That means somebody have changed the name. So what you can do manually, you just change the name. So let's do what the control one, or patient, whatever you wish. Well, we do a patient or control? The what is the file name? It's DOC patient. So this which we have. So once you select, it will ask you what the best name you want. So always when we, it's good practice, we give all the EEG files in a similar kind of index, like a subject 001, subject 002, or your experiment, for example, BRH 001, BRH 002. So you can import all these things and make loop so all these things are like a DOC patient 001, like this. And so this will be your prefix followed by all the things. And when you import it, do, as I said, it will do all the pre-processing steps. So it's first downsample to 250 hertz, and well, it do all it imports the data and the channel location, down sampling. Before down sampling, it also discarded 73 electrode, which is the face and neck, and it do the filtering and bad channel detection. So if you see here, it's written what he have done. So first 84 channels are removed. So these 84 channels are what is face and neck. Then did the down sampling, and then it did the low pass filter with 45 hertz and high pass filter with 1 hertz, and then notch filter with 50 hertz notch filter, and then it epoch whole continuous to the 5 sorry, in our condition 10 10 second. So what we can do, we can discard a specific epoch where it is noise, and it also detect which channels are noisy channel. So this automatically detect, and it says okay, there are our 52 channel is having noise, and out of 93 yeah, epochs, uh, whole EEG divided to 10 10 second. So out of 10 10 second 93 epochs, there have a 15 epochs. So in our MOHAWK pipeline, we basically contain the 10 minute of data, which is 60 epochs, every epochs for 10 seconds. So 60 epoch. And when you discard the channel, automatically you first discard only few. So for example, 10, you select 10 channel to be removed, then visually you look and you remove if there are really so many channel. And if any data you have manually as well as automatically more than 40 50 channel, we doesn't consider, we doesn't do this EEG for analysis, because if you discard 52 number of channel, so the connectivity, or it will be incomparable, and it will also do the interpolation. So when it do interpolation, it generate 52 number of channel dummy channels which have a high synchronization. So that's a drawback. So to what is increase the threshold, you just give some value like 1400. So when you 1400, there is 40 channel, right? And 3000, 29, and 5000, 28 channels. Still. So this data is very noisy. Good. 15,000, 21. Around 18 channels. So I in EEG I do not discard more than 25 channel, and in brain product I do not discard more than 15 channel. But again, it's open you key. If your data is so much important, then you try to make balance, discard some channel, and discard the noise in ICA. And here you see 93, and what I do here, I keep like 60 60 sorry 65 70. So now if out of 93 20 are discarded, that means 80 3 are there. So I just a little bit more, 900. Yeah, 26 means still I have data. we're supposed to have a 60 epochs. If it is less than 60, like a 50 or 55 holes, it's not a problem. But if you have a 30 epochs, then it's a problem. It's and less than 30 is quite difficult. And if you see the data is really look noisy, then I have a uh, here. So to visualize better, what I do, I divide the whole channel to so I out of 172, I keep 90 so I can visualize the EEG channels better. And here, if they have a higher fluctuation or they have a high frequency, so the amplitude or the frequency that this is noise. So you could see here higher amplitude fluctuation is there in the early time. Yeah. So to discard that one, you just need to click once, and to deselect. So let's assume this one, I think, okay, this is good. I doesn't need to discard. You just click again, right click. So it's noise, and here you have a high frequency as well as high amplitude. Then you discard, and so when I goes, I first look also on the what is number of which channel have a higher noise, and you could see this channel, it have a higher amplitude fluctuation and also high frequency, this content, and this is not what is coherent with the other channels or in the neighbor channel. So that means it is the noisy channel. And to discard that, I right click and here toggle the bad channel. Sometime when you toggle, instead of this, it's actually deselect the what is neighbor one. So it's the same way to what is again reselect. So let's assume instead of wrongly you did the above one, to reselect, again right click and again you toggle it. Toggle it means you switch the channel as in noise to good channel or good channel to noise. So this channel is a bit noisy.
Sorry, Rana,
And
the channels with the red triangle are those that are
yes,
bad. So those we exclude.
yes. So now, like when I was again discarding, it was uh, wrongly selected. So I deselect that one, then I try to. Yes, perfect. So I have so we out of 93 we had already discarded 26. So that means we have now around 65 channel. So we didn't have a liberty to discard so much. If you had this liberty, I supposed to be discard this, but as we have a lesser, so I don't discard this and I'll discard this one because they have a high frequency fluctuation as well as the amplitude is higher. And probably this channel is a completely noisy channel. If you go again one more, so when I also discard a channel, I don't discard looking only 1 or 5 epoch. I looked 20 to 30 epoch. So you could look actually 20 to 30 epoch if there are that channel is persistent for 20 to 30 epoch, then or not 20 to 30 epoch, more than 10 epoch, then you discard. So this channel which have a noise in this channel also, but here you could see here that have a higher noise. Discard. And this channel, let's see some more. Yeah, these two channel is very near to each other, and it's have Like this, you goes on, you visualize all the epochs, and you discard where the epochs have a noise. I'm not doing very thoroughly, but when I do, I spend little time here and in the ICA to discard all the noisy reports, and also make the balance that I supposed to have a minimum 50 epochs, that is 9 minutes of data. So like here also it is. This is how and this channel here, three channel, you see, this is also one of the things. When you discard the channel, you must be aware that you didn't supposed to be discard so many channel nearby. So like here, if I discard this channels, that means I'm discarding the neighbor three channel. So when it will be doing interpolation, it will be creating a like what it is called, and the interpolated channel will be created from the same discarded channel, so it will be having a higher on homogeneity. So this on homogeneity creates sparse result, especially when we do connectivity or graph theory kind of analysis. But I see this channel is persistent in all the epochs. So yeah, that's why I discuss. It's okay to discard like a three or sometimes four, but if you have like same never channel, 7 8 channel, then it will be a big problem. You should not discard 7 or 8 channel nearby. This reference I'm giving you with respect to EGI, which have 256, or after discarding 173 channel. When you are doing the brain vision, you will be again more leisure, and when you are doing a 32 channel, you should not delete like more than 3 or 4 channel. You will not have a more 3 or 4 channel noisy channel, but in if you have like out of 32 channel 4 channel or more than that, then it may issue. For power spectral, the normal analysis, or when you look the whole brain analysis, like Lampertje, for in that situation, it's not a big problem. But when you are doing a local analysis, like pairwise connectivity or any information network theory analysis, it's a big issue. So that channel discard is much important. So I goes like this. Yeah, I'll move. We have already. Then, as the same, I looked in the web channel. I also looked the lower channels, and I discovered if they have a very high noise. And this one, this channel, you could see it's having a high noise. So, yeah. So I don't go over all, otherwise it will take more time. So after you select all the noisy channel and noisy epoch, then you just update, and it will ask you to rewrite or not. You could rewrite, because you doesn't need to be create all, and it's also take a lot of data sites. So, and then it will do the ICA on the downsampled, pre-processed, and good epoch and good channels data. And in the ICA, we do further noise reduction, which have a bigger impact. For example, ocular artifacts. So ocular artifact from by visually, it's little difficult to discard. And when you discard also, like out of 10 minutes, it will you will be discarding like 2 minutes or 3 minutes. And muscular artifacts, so most of the time when we record there have eye ear pinch, and those noise we discard from the ICA. But as Pablo was saying, the EGI lab or not, he suggests don't do anything. So I think with my view, it's not correct. We at least discard the EOG artifact and muscular artifact, which is very clear from power spectral and from the what is EOG from the channel you can clearly see. So you should discard at least that two kind of noise. So let me tell you now how to do the ICA. Here I wrote also the step by step, so you could follow. Uh, so in EEG lab, it gives the three things. One is your the ICA time series, ICA spectral map, ICA power spectral, and this one is the same as the time series, but in the form of activation. So you could see, okay, this component is coming from some particular epoch or in all channel. How do I use? Yeah. So for example, this component is from all over the and in the x-axis it is epoch. So we have 60 epoch in that data, and here it is the 10-second data. So you could see the activations, the higher activation is all over the channel, all over the epoch. And sometime, for example, yeah, for example, in this muscular artifact or in this, it is only few places like this epoch, this epoch, this epoch, not overall, and here also. So we first gives the high importance to the spectral map. In the spectral map, we see, okay, is it a clear, it is kind of cluster, or it's like some noisy component. I'll show you how noisy component. Then we give the, we look also the time series and power spectral. By taking consideration of all three, we still we take the decision that this ICA is a noise ICA or it's what is signal. So in the noise ICA, the main thing is ocular. So you and ocular artifact always you will find in the top 3 or top 5. And if you see in the signal, there have any like what is sinusoidal or like a peaks, bigger amplitude peak compared to other channel. You can you think that okay, this may be noise, and you just look it in the power spectral, and you will find it clear. Okay, is it a ocular artifact or not? In this condition, it's kind of ocular look like, and the ocular artifacts will be look like this on the top of eye. And when you look the temporal signal, ocular artifact will be very clear in the temporal signal also. It will be like this high amplitude, high fluctuation amplitude, and consistent in every 2-3 epoch, or every epoch you will find this high amplitude fluctuation. And it could be positive like this, or it could be negative also like this. Ocular artifact by viewing the EEG, sorry, ICA time series, and by this you will be able to understand very clearly. And even if the power spectral is very good, like here, the power spectral look like so well, but you're supposed to be discard that. And second is the what is muscle artifact. So it's basically you will see like a very high fluctuation at year or completely red or blue. And when you will also look the power spectral, it will be noise. And this, if you don't discard also, it doesn't make a much effect. But the much effect is this one, or this kind of, when you see the power spectral, if there have a sudden sudden dip. I see in the EGI as well as in the brain product, in healthy individual as well as in patient, we find this kind of pattern very well. So, most of the subject. So if there have a sudden dip, especially in 10 hertz, and after 40 hertz, there is a very high peak, that is a noise, and you could see it will be localized to central, or it will be localized somewhere. And when we see in the time period, it will be like in a particular channel, or not smooth. And I'll show you some more of this pattern, which it is still running. So like this pattern, when you see, it will be localized, and it will be mostly also like a positive to negative. So if you, in the spectral map, if you see like a negative cluster and positive cluster, it doesn't happen in EEG. And there is a high dip, sudden dip in both 16 and 31. It's a one subject where I find this kind of tool. It's another subject you see. So this kind of things, if you are finding in the this, yeah. So when you see this kind of power spectral, then you consider it's noise and you discard it. So then the good ICAs are like this. So it will have a alpha frequency, and in DOC patient you will not see a alpha alpha and beta frequency, but it will be like this kind of a smooth little peak in the 10, around 10 hertz. And there will be a big cluster, positive or negative cluster. So these are the good IC's component, and this component will be across the epochs, like this, unlike here what you see. These are the good epoch where you see all the activation across the epoch, across the time series. Wherever the bad will have like this or like this. I'm showing you some example, but you can also find. And here Pablo already explained you in details. Here some of the noise, how the power line and cardiac activity, and muscle and muscular activity and ocular activity. So sometimes you will able to see a big amplitude peak when eye open condition, you can see like this, and in eye closed condition it will be, you will be like able to see like this. It will be the spectral map will be like this, so you can see. And when you'll be doing the data analysis by doing only, let's see, yeah, it's done. So after pre-process done, oh, time is really going, I need a little bit fast. So we have a little bit more time, or not? How much time we can sit? Can we sit like at 2:15 also?
We have a meeting, so we leave anywhere.
Oh, okay. So let's then I finish in another 8 minutes. I don't know we'll be able to finish or not. So here, as I said, you need to see the first from the time series, and in the top 1, 2, 3, there will have a EOG artifact. So you could see the IC component 1 and IC component 3, they have a high amplitude fluctuation, and it is also periodic. So if something is periodic, that is noise. And you see the 12 number channel. So by just looking couple of what is time series, we first see, okay, 1 3 sorry 1 4 12 is kind of noise. And then we go and to see here, and you click here, and you so here you see your whole brain, and it is for particular region. But in the time series, it was very clear there have a higher amplitude and a periodic. So discard this. And when you discard, also use out of 35, try to discard 10 12, not much. In patient, there is or when we have a higher noise in the signal, you will be finding so much IC component to be discarded. And if you are discarding like a lot of out of 35, like 20 channel, you'll be aware that okay, that could be influence your result also. So 12 we go down like this, and we see yeah, this is sudden little bit and near to here, but the power spectral and the epoch look like good. But here it is like you see here this it is very periodic in all. So then you one by one use visit, and you see when you also see the power spectral is very zigzag. This is little okay. Sometimes I see like zigzag here, sinusoidal wave kind of things that we discard. And these things I have written here. Maybe you could just go through different noise component, how it's look like, and you discard. So for the time, I am discarding only this much and going. But like there will be so many noise IC component which we supposed to be discard like this. So after you choose which are the noise component, you select OK, and then you update. So you see this is the EEG lab structure. So all we are doing pre-processing now in the EEG lab. And then update EEG structure. When you update, it will again show okay, how many is there have again some noise channel and noise epochs. So like here, so it's showing only one epochs which have a noise, and how many 13 channels still have a noise. So here you could discard one, but try to keep some more channel. So like because we have already discarded 2022 channel, yeah, 806 channel, and this looks like a very high variance. So even sometime I discard some less like 25. And so here the currently what we are using is the MOHAWK GUI. You can also do in the pipeline. So in the MATLAB code where all the steps are executes, it's MOHAWK .m. You can open that one, and sometime when we have a what is a new EEG channel data, there have a problem in the channel. So sometimes it renamed wrongly, or sometimes the channel was broken, data was not there. So it will give you a error, and that channel mismatch, or X number of channel does not there is not there. So you can go manually to here yes, data import. In the data import, you check which channel is not there, or which channel is renamed wrongly, or misplaced, means broken, and that channel you manually exclude, and you could interpolate, or you could do whatever is required. So this data, when a channel problem or data import problem is there, you can find the solution from data import. Then what I do, for example, you have done once analysis, then you see, okay, my pre-processing is not done properly. You can run from the manual selection. So here to select all, you can have like two percentile. When you do 2 percentile symbol, it will make all in one section. So after doing all as a one section, then run by run selection. So it will run only the what is the lower the IC component onwards. So you didn't need to go from the starting onwards. So you save the time. So, when there have a high number of noise, or I discarded a lot of epoch and channel, what I do, even if I do one time again, I look the ICs and discard one or two and see how data is changing. So if when discarding one IC you see a big differences, then it's also a marker of its the noisy data, because it's not by discarding just one epoch, the result should not be changed in a very high level. So that's you could do. And then all the post processing, as I said, it do automatically. So here we use power spectral using calspec. So it's compute the relative power, and the relative power is, I could show you here, for every channel. And so it generates like this. So every graph is one channel. So this is a healthy subject, and you could see the alpha and beta. There have a higher alpha and beta, and this is a typical pattern for a healthy subject. We compute this using the function of EEG lab. Then we do the connectivity analysis, which is again done automatically. 50 already. So this FT coherence, in the FT coherence, if I go, yeah, it's already done. So as Pablo was saying, there have so many different types of connectivity analysis. Even if the paired connectivity analysis, there is I think more than 10 different types, and most popular which is people use is the PLI, phase lag index. So it takes the phase of one channel to another channel, and at every time point it see how much phase are correlating. And then on the PLI, then there have a problem of what is volume conduction. So in EEG, when we do connectivity analysis in the SCAP level, many people highly criticize for volume conduction, and it's true also. Like when you discarded 3 or 4 channel, the volume conduction increases very highly. So to counter this, the DWPLI, which we use in this, and many studies have done research, and they show that the DWPLI is a little handle volume conduction well. But other than we use here DWPLI, the direct field trip function. What is field trip function? That is FT connectivity. Other than the DWPLI or WPLI, there is a PLV. There is a synchronization likelihood, and there's some like 10 different kind of pairwise connectivity we have. And for the effective connectivity, recently it's very popular in this effective connectivity. And early stage for EEG, people who are using the Granger's causality and dynamic causal modeling. But now transfer entropy also picked up, and many people are using transfer entropy, multivariate transfer entropy as a effective connectivity. Then we have graph theory. So in MOHAWK we use around 10 different graph theory measure. The most popular are degree and brain integration segregation. In consciousness, I think all spectrum, including coma, anesthesia, meditation, hypnosis, all over, all whatever these consciousness related studies are there. They have shown that brain integration and segregation is one of the measure which distinguish different states, and it also characterize the conscious level. So we also use here integration measure from participation coefficient, and a segregation measure from clustering coefficient and modularity. So I have a good image here. Yeah. So this is a representation. The connectivity will be pairwise connectivity, one region to another region. So brain region to region. So this brain region to region, we first do a specific threshold. We take only the higher which have a higher connectivity above to the threshold. For example, 30% more, and we project this connectivity to the head plot. So here, just to have a better view, but it's just a visual representation. And in the head color is the degree. So each region, how many connections are there. But connectivity itself, it just gives a statistical relationship. But how these connections are organized, that we can understand from network theory. So for example, there have this much of connections. Some node are connected to some other node, but how this connected node are organized across them, that we could use using a different graph theory measure. So for example, how well the connections are clustered, and that we could see from the modularity or clustering coefficient, and how well these clusters are integrated across each other, that we could see from the integration. As well as let us assume there have so many brain regions which have a connectivity, but which brain region is having a long range connection, having a short range connection, which brain region are region to connect different modules. So for example, this region having a higher connection to 1 2 3 4 5 6, but this is local, it have a local connection, doesn't have a long range connection, or doesn't have a different module or different cluster connections. Whereas these connections, the red one is having within the cluster as well as other module, like this module and this module. So it's connecting three different module or three different connections, and it will also have a long range connection, like from here to 1 2 3. And whereas this electrode have only one connections. So this also gives characterize how the connections are there. And when we characterize from a network perspective, it gives an underlying mechanism, like okay, the integration the connectivity have decreased or increased, but how what that increased connectivity mean, or what that decreased connectivity mean. Is that breaking down the long range connections, or is that breaking down the short range connection? Is that weakening the information or what is prediction of the neuronal flow? So this we could see from the graph theory, and now information theory also evolved, and many people are, including we, use in consciousness that information flow is one of measure which not only distinguish, also characterize the mechanism. So yeah, if you, we are already 57. So yeah, it gives like this connectivity, and it also gives the graph theory. I think I used a new version which doesn't produce that image, but it produced the image of this. like this. So here we just picked up the most sensitive one, that is the participation coefficient or network integration, also called network centrality. These are different names, but in almost all consciousness, including DOC, it have shown that this measure is the network centrality, one of the sensitive measure. That's what we just picked up, and we see the UWS patient have a lower network integration compared to that. And yeah, that's all of the con. But I can also give you those some of the code for statistics. So this is the MOHAWK is only one subject pipeline, but you can what is extract this time series. Sorry, extract these results. These results will be stored on the name of the what is MOHAWK. So what we have done now, pre-processing and post-processing. The post-processed data, the pre-processed data will be the base name, that is a DOC patient dot is FDT and DOC patient dot uh, set and FDT format, where EP blah blah blah. Let me show you. Yeah, so this patient we we did the DOC patient, this patient now we have done it. So after all pre-process, the pre-process data will be stored in this DOC patient, FDT and ACT. This is a clean signal. And this DOC patient MOHAWK, here all your post-processed data is stored. So for example, here the power for all channel 173 channel and 5 different frequency bandwidth, that is alpha, beta, delta, theta, and channel WPLI. This is nothing but your that connectivity map, which 173 into 173, which you this 173 no, sorry, yeah, here it is, sorry, matrix. In the matrix for every frequency band, alpha, beta, delta, theta, 173 into 173, and the graph measures, those are here. So it's stored in the this variable, that is clustering coefficient, path length, global efficiency, modularity, centrality, modular span, degree, all this. And the most important are the degree, clustering coefficient, global efficiency, and modularity. But you could check if you are doing some study research, you could check all. And sorry, again, participation coefficient. The participation coefficient is the network centrality or network integration. And then you could also look the what is brain region wise, like in this study which we have shown. Like here we see, okay, there is an increased connectivity, or there is a decreased connectivity, but which region or which lobe, lobe to lobe, that you could see also by looking in the different network. And we also looked in the DOC and apnea, and I recently looked also in the what is hypnosis. There is there is good differences. So when we see here, we can say that okay, the connectivity was increases or decreases. But when we see which lobe, we can more talk about okay, there was a midline reduction or there was a frontoparietal reduction. So it's also a good way and good representation when we discuss the connectivity pattern. So this is also one kind of which you could do it from the connectivity matrices. Yeah, so we are already 3 minutes late. I was thinking that I'll be able to get time to show you the ERP, but I think we could sit once more. So there is this paper recently we published. So we have developed the pre-processing as well as post-processing pipeline, where we can see the ERP component like as like Pablo was showing for auditory. Here we have for what is in pain stimulation, but it's same as and it's high density 256 channel EEG. But we could do also any EEG machine, and it will show you the ERP component both at individual subject level as well as at the group level, and it will show in the topo plot also which channels are significantly different. And you could also do the lobe wise frontal parietal blah, blah. And you could also see the power spectral. So here like time after stimulation and frequency, and you see okay which frequency there have differences between two conditions and which electrodes have differences. So I was thinking I will be able to present, but one another day.
Next time.
Yes.
Thanks, Dr.
If you have some question, then we could discuss. No? Okay. Thanks, guys. Which I need. Leave.
Or
You just go ahead forever.
stop recording.
Okay.
And then don't leave the meeting, but finish it.
Where,
Stop,
No,
stop, yes.